Hello friends, in this video I am going to talk about symmetric group Sn. So let's first talk about permutations. So fix an integer n greater than equal to 1 and consider the set S, which is all the numbers from 1 till n. Now a permutation is basically a 1 and onto map from the set S to S. Okay, so it is called a permutation because basically it permutes the numbers 1 to n. So let's take an example and try to understand. So we have fixed n equal to 5 and I am defining this function f from s 1 2 3 4 5 to s itself as, so my numbers are 1 2 3 4 and 5. I'm sending 1 to 3 under the map f, 2 to 2, 3 to 1, 4 to 5 and 5 to 4. Okay, so this is my function and you can see that it is 1 and onto it covers all the numbers 1 till 5 in the range. So a concise way to write this function if is, you write in the first row, you write all the numbers 1 2 3 4 5 in that order, and in the second row you write where these elements are being mapped to. So 1 is being mapped to 3, so below 1 you write 3. 2 is being mapped to 2 itself, so you below 2 you write 2. 3 is mapping to 1, so 3 below 3 you write 1, then 4 to 5 and then 5 to 4. So we can write a permutation like that. So if you fixed n, there are n factorial permutations from the set 1 2 3 till n to itself. So how can we see that? So you want a map from S to S, right? Which is 1 and onto. That's a permutation. So you want to map 1 to some number. How many choices you have? You can map to 1 or 2 or 3 n. So you have n choices. So for 2 now, since you have mapped 1 to some number already, for 2 you have n minus 1 choices. Similarly for 3 you have n minus 2 choices, and when you go till n you are only left with one choice. So if you multiply n times n minus 1 times n minus 2 till 1, you get n factorial. So there are total n factorial permutations from the set S to S, where size of S is n. So let's take an example. So if n equal to 3, there are 3 factorial, that is 3 times 2 times 1, 6 permutations. And in this above notation, all these permutations can be written like that. So this is called the identity permutation, where every element is fixed. 1 is going to 1, 2 is going to 2, 3 is going to 3. And then there are other 5 permutations on the set S equal to 1 to 3. So now since we know what permutations are, we are ready to define the symmetric group Sn. So again fix n, then all permutations from the set 1 2 till n to S itself, they form a group under composition of maps. And of course the order of the group will be n factorial because there are total n factorial permutations, and this group is known as the symmetric group Sn. Okay, so to understand what the binary operation is, which we are saying is composition of maps, let's take an example. So consider the group S3. So we have fixed n equal to 3 and we are taking these two permutations where 1 is going to 1, 2 is going to 3 and 3 is going to 2, and we are composing it with another permutation where 1 is going to 2, 2 is going to 1 and 3 is going to 3. Now the result will be another permutation, and how will we get that? So in this 1 is going to 2, and then here you see that 2 is going to 3. So your 1 will go to 3 in this permutation. Okay. Similarly, here 2 is going to 1 and then 1 is going to 1 itself. So 2 will go to 1 in this permutation, and similarly 3 is going to 3 here and 3 is going to 2 here. So 3 will go to 2. So that's how you get the new permutation. So you have to be careful that the way you compose functions and permutations are functions, you start the composition from left. So you go from left to the right. So there are two very important properties about the permutation group Sn, that it is a non-abelian group or non-commutative. That is, you can always find elements A and B in Sn, two permutations, such that A composition B will not be equal to B composition A, and it's not very hard to see. Also, it is a non-cyclic group. That means you can never find a element in Sn or a permutation in Sn whose order is n factorial. Okay, so elements or orders of all permutations in Sn will be strictly less than n factorial. Okay, so before we look at other properties of the symmetric group Sn, a word of caution that the set S which we have taken to define permutations, the set 1, 2, 3 till n, is just to ease notation, and this set S can be replaced by any other set of size n to define the symmetric group Sn. For example, if we take S to be alpha, beta, gamma, and we define all permutations from S to S, it will still be the symmetric group S3 because the size of set S is 3. So let's define a cycle. So a cycle of length k is a permutation, and we write it like this. So there are k symbols a1, a2, ak minus 1 till ak, and what it means that under this permutation a1 is mapped to a2, a2 is mapped to a3, and then ak minus 1 is mapped to ak, and then ak is mapped to a1, so it comes back to a1. So that's what we mean by cyclic. So let's take an example. Let's 2, 4, 1, 3 be a cycle permutation on the set 1, 2, 3, 4. It means that 2 is being mapped to 4, 4 is being mapped to 1, 1 is being mapped to 3, and 3 is being mapped to 2. So you know where all the elements 1, 2, 3, 4 are going. So basically you can see that 1 is going to 3, 2 is going to 4, 3 is going to 2, and 4 is going to 1. So it's the same permutation, but we are writing it as a very simple notation 2, 4, 1, 3. Of course, so then the next question is, can we write any permutation as cycles? So the answer is no. For example, you take this permutation, 1 is going to 3, 2 is going to 2, 3 is going to 1, 4 is going to 5, and 5 is going to 4. This you can't write as a cycle of length 5. Okay, but something in this regard is true, which we'll see next. So now we'll learn how any permutation can be decomposed in cycles. So first definition, we say that two cycles are disjoint if there is no number common between them. So let's try to understand using an example. So 2, 3, 4 is a cycle of length 3, and 1, 5 is a cycle of length 2, and 3, 5, 6 is a cycle of length 3. Now 2, 3, 4 and 3, 5, 6, they are not disjoint, right? Because the number 3 is common between them. But 2, 3, 4 is disjoint with 1, 5. Okay, because here the numbers are 2, 3, 4, and here the numbers are 1, 5, so there is nothing common between them. So now we have this result that every permutation can be written as composition of disjoint cycles. Okay, this is very important, disjoint cycles. So how can we do that? Suppose a permutation is given to you. So what you can do, you start with 1, and let's say 1 is being mapped to a1. So you start with 1 and 1 is being mapped to a1. Then you see where is a1 mapped to. Let's say it is mapped to a2. Okay, and then you keep going until you hit ak such that ak is mapped to 1. Then you complete one cycle. Okay, now you see that what is the smallest integer bigger than 1 which is not here, okay, which is not in 1, a1, a2, ak. You choose that number. Let's say that number is b. Okay, and then you again do the same thing. Where is b going? Say b is going to b1, then b1 is going to b2, and you keep doing this until you exhaust all the numbers 1, 2, 3 till n. And suppose if a number is mapped to itself, like say 2 is mapped to 2, then we do not include it in the cycle notation and it will be excluded. So suppose you have permutation written as decomposition of cycles and some number from 1 to n is not appearing in that decomposition, then you know that that particular number is fixed by that permutation. So let's take an example of this permutation in S5. So the permutation is 1. So we start with 1. Now 1 is going to 3. So we write 3. Then 3 is going to 1. So the first cycle is done. Now what is the number bigger than 1 which is not included here? 2, right? So then we take 2. 2 is being mapped to 2. So we don't have to write it. Now what is the next number which is not included? 3 has been included. So next is 4. Now 4 is being mapped to 5 and 5 is being mapped to 4. So we are done. So this is the notation decomposition into cycles for this permutation which is given to us. Okay, so far we discussed that permutations on the set 1, 2, 3 till n form the group symmetric group Sn, and any permutation can be written as composition of disjoint cycles. Now we'll use this fact to calculate orders of permutations in Sn. So what is order of an element? So you take the element G and you start composing the element G with itself. So G composition G 2 times, then G composition G 3 times. So G composition G, G composition G composition G until you reach identity, like doing that. Okay, so to shorthand we write like G square G cube. So what is the smallest integer k such that G to the power k is identity, and that k will be called order of the permutation G. So let's try to understand using an example. So G is this permutation in S3 and its order is 3 because G composition G is this permutation, and of course it is not identity because 1 is going to 2. But the moment you calculate G composition G 3 times, you get 1 is going to 1, 2 is going to 2 and 3 is going to 3. So this means G cube is identity and 3 is smallest such as integer, so order of G is 3. So it is not very hard to see that order of a cycle of length k is k. So for example, if you take this 3 cycle, that is a cycle of length 3 in S5, its order is 3. So 2, 4, 5, if you compose it 3 times, it will be the identity permutation, that is 1 is going to 1, 2 is 2 and 5 is to 5. So now we know that order of a cycle is its length. So now take any permutation G in Sn and let it can be written as C1, C2, Ck as product of disjoint cycles, and length of C1 is L1, length of C2 is L2 and length of Ck is Lk. Then order of G in Sn is LCM of these lengths, LCM of L1, L2, Lk. So let's try to understand using an example. So if you take this decomposition of some permutation in S10, you can see that, so it's very important that all cycles are disjoint. You can see that all cycles are disjoint. This has length 2, this has length 4 and this has length 3. So the order of this whole element will be LCM of 2, 4, 3, which is 12. Okay, so now we'll see how partition of an integer n greater than or equal to 1 is related to the cyclic decomposition of a permutation and hence to order of the permutation. So what is partition of an integer? So it is a way to write n as a sum of positive integers. So what are all partitions of 5, for example? So one partition is you can write 5 as 1 plus 1 plus 1 plus 1. Another is you can write 1 plus 1 plus 1 plus 2. Then 1 plus 1 plus 3, then 1 plus 2 plus 2, 1 plus 4, 2 plus 3 and just as 5. So you can see that there are 1, 2, 3, 4, 5, 6, 7 partition. There are 7 partitions of 5. Okay, so now take any permutation G in Sn and now look at it decomposition in disjoint cycles. Now using this decomposition you can associate G to a partition of n. Let's see how. So let G be in S5 and it has cycle decomposition 1, 3 and 2, 5, these two cycles. Then we associate it to the partition 1 plus 2 plus 2 of 5. How? So these are two cycles, 2 and 2 comes from here, and you can see that one number 4 is missing. So of course 4 is being fixed by the permutation G, so that gives us 1. So 1 plus 2 plus 2, we associate this element to this partition. Okay, so now given any element G in Sn, we can associate it with a partition of type A1 plus A2 plus dot 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 AK. Then the order of the element G is nothing but LCM, and you take LCM of all the parts in this partition. For example, we took the element G, which is given in disjoint cycles as 1, 3 and 2, 5. So it will have order. What are the partitions? It is associated with partition 1 plus 2 plus 2. Then the order of G will be given as LCM of the parts 1, 2, 2, which is 2. And of course, take any partition A1 plus A2 plus dot 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 AK of n. You can always find element in Sn, that is a permutation, which is associated with this partition. For example, take the partition 2 plus 3 of 5. In fact, you can find many elements in S5 which are associated with this partition. For example, 1, 2, 3, 4, 5. So this gives the 2, this 2 cycle, and the 3 cycle gives us the 3. Similarly, 1, 3, 2, 5, 4. This first cycle gives us the 2 and the second cycle gives us the 3. So they are associated with the partition 2 plus 3. Okay, so now you see how partition of the number n is associated with the order of a permutation. Now again, using this fact, we can find maximal order of elements of Sn. So Sn, we know that is not cyclic, so there is no element with order n factorial, that is the order of the group. Then what is the maximum possible order of an element in Sn? Okay, and there is no formula as such for this, but using partitions of n, we can find it individually for any Sn. So how can we do that? So let's take an example. So again, partitions of 5, we saw there are 7 partitions, okay, given by these. Okay, and now we can try and find that for each partition what will be the order of the element. So if you take the partition 1 plus 1 plus 1 plus 1 plus 1, if some element is associated with this partition, its order will be LCM of 1, 1, 1, 1, 1, that is 1. Okay, now take this partition 1 plus 1 plus 1 plus 2, then LCM, then order of the any element associated with this will be 1, 1, 2, that is 2. Similarly, for 1 plus 1 plus 3, the order would be 3. 1 plus 2 plus 2, the order would be 2. 1 plus 4, the order would be 4. 2 plus 3, the order would be 6. And for 5, the order would be just 5. So you can see the maximum possible order of an element in S5 would be 6. So suppose you have a Sn given to you. Now the number n can have many partitions, and suppose the question asks you to find what is the maximum possible order of an element in Sn. So now how can you quickly look at some partitions which might give you the maximal order? So you should find the partitions in which the parts are relatively prime to each other. For example, you saw that in case of S5, 2 plus 3, here 2 and 3 are relatively prime to each other. this gave you the maximum order 6. Okay, so let's take another example and try to see how this works. So n equal to 8, it has many partitions, but I'll look at partitions which, the parts are relatively prime, and one such partition is of course 1 plus 7 is 1, 3 plus 5 is 1. Okay, and 1 plus 2 plus 5 is 1. You can look at them, and 1 plus 2 plus 5 will give you the order 10. 5 plus 3 will give you 15, and 1 plus 7. So you can see that 3 plus 5 is the partition which will give you the maximal order 15 in a set. And one such element you can find, you have to find a 3 cycle and you have to find a 5 cycle, and this is one such element with order 15 in a set. Okay, so after discussing these concepts, let's try to solve some problems. So this question came in JAM 2016. So it says that let sigma be a permutation in S5. What is the maximum possible order of sigma S? So this in fact we already discussed. So 5 has partitions, 7 partitions, and the partition which will give you the maximum order is 2 plus 3, and so LCM of 2 comma 3 is 6, and 6 will be the maximal order here. Again, a similar question came in JAM 2017. What is the maximum order of sigma in S10 is? So let's look at some partitions of 10 which might give you maximal order. So we are looking at partitions in which parts are relatively prime to each other. So some such parts you can see is, for example, 3 plus 7 or 3 plus 2 plus 5. Okay, and yeah, so these two immediately comes into mind, and I don't think any other partitions will beat them in terms of LCM. So the LCM of 3 and 7 is 21, and LCM of 2, 3 and 5 is 3 times 2, 6, 5 is 30. So the maximum possible order in S10 is 30. Okay, so this next question which came in JAM 2018, it is completely based on permutations, and as I said, sometimes you can get sets in which permutations are not defined on 0, 1, 2, 3, but some other set. So here the permutations are defined on alpha, beta, gamma, delta, and these are 3 facts given about F, G and H, and depending on that, it asks that which of these following permutations interchanges alpha delta. So alpha goes to delta and delta goes to alpha, but fixes beta gamma. That is, beta will go to beta and gamma will go to gamma. Okay, so let's take each of these permutations and see what's happening. So let's take this first permutation. Now alpha, what is happening to alpha? So under F, alpha is going to beta because F interchanges. Then under G, beta is going to gamma. Then under H, gamma is going to delta. Then under G, delta is going to delta. And then under F, delta is going to delta. So in this, alpha is going to delta. Okay. And what is happening to beta here? So beta is going to alpha under F. Under G, alpha is fixed. Under H, alpha is fixed. Under G, alpha is fixed, and under F, alpha is going to beta. So beta is fixed, and similarly you can see gamma. So under F, gamma is going to gamma itself, and then under G, gamma is going to beta. Under H, beta is going to beta, and under G, beta is going to gamma, and under F, gamma is going to gamma. Okay, so then you know that delta in this case will go to alpha. Okay, so it does interchange, alpha is going to delta and delta is going to alpha, and it fixes beta and gamma. So definitely this permutation does the job. Now let's look at the next permutation, this one. So you can see that So let's see where alpha goes under this permutation. So g of alpha is fixed by alpha. Now h of alpha is also fixed. Now f of alpha is interchange, goes to beta. Then h of beta fixed, so beta. And then g of beta is gamma. So alpha is going to gamma, which we don't want. So this can't be permutation. Now look at this. Again, we see alpha. So g of alpha is alpha, f of alpha is beta, h of beta is beta, f of beta is alpha, and g of alpha is alpha. So alpha is going to alpha, so again we don't want that, so this is not an option. Now let's look at this. So in under this h, under h alpha is going to under h alpha is going to alpha, alpha is going to alpha under g, then alpha is going to beta under f, beta is going to gamma under g, and gamma is going to delta under h. So alpha is going to delta. So far it is fine. Now let's look at beta. So h of beta is beta, g of beta is gamma, then f of gamma is gamma, and then g of gamma is beta, and h of beta is beta. So beta is fixed, which is again good. Now let's look at gamma. So h of gamma is delta, and g of delta is delta, and f of delta is again delta, and g of delta is again delta, and h of delta is gamma. So gamma is also fixed, which is good. And then last element which is left is delta. So h of delta is gamma, and g of gamma is beta, and f of beta is alpha, and then g of alpha is fixed, so alpha, and then h of alpha is fixed, so alpha. So delta is going to alpha. So yes, alpha delta is being interchanged and beta gamma fixed. So this is also a correct answer. So here answers are 1 and 4. Okay, so this question came in JAM 2018 and it asked the order of this element in S6. Now you can make a mistake and say that okay, 3 3 3 and LCM of 3 comma 3 comma 3 is 3, so the answer is 3. But you have to be careful and see that this decomposition is not disjoint. These are not disjoint cycles. So first we write the permutation. So 1 2 3 4 5 6, and we see where 1 2 3 4 5 6 are going. So 1 is going to 2, then 2 is going to 4, and 4 is going to 5. So 1 is going to 5, then 2 is going to 3, and 3 is fixed in the later one, so 2 is going to 3. Now 3 is going to 1 in the first one, and then 1 is fixed, so 3 is going to 1. Now 4 is going to 5, and 5 is going to 6, so 4 is going to 6. Now 5 is going to 2, and then it is fixed, so 5 is going to 2, and then 6 is going to 4. So this is the permutation which is written in this form. Now we write it in terms of disjoint cycles. So you start with 1, 1 goes to 5, 5 goes to 2, 2 goes to 3, okay, and 3 goes to 1. So this is where it stops. Now 1 is there, 2 is there, 3 is there, 4 is not there, so we start with 4 now. 4 is going to 6 and 6 is going to 4. Okay, so the all numbers are there. Now it is in terms of disjoint cycles. This has length 4 and this has length 2. So LCM of 4 and 2 is 4. So the order of the element is 4. Okay, so a similar question came in JAM 2019 where you have a 100 cycle 1 2 3 till 100, and Y is a 2 cycle 49 50 in the group S100, and then it asks about order of XY. Now you see that 49 50 is already in this 100 cycles, so XY are not disjoint cycles, right? so we can't really take LCM right away. So first we need to write xy as product of disjoint cycles, and then we can find the order. Okay, so let's find what is the permutation xy. So we write as 1, 2, 3, and you see 49, 50 is bit, so we need to write all the elements. So 48, 49, 50, okay, 51, and then we go dot 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 till 100. Okay, so I'm trying to write xy. Now you see 1 is going to 2, okay, and 2 is going to 2 in this 2 cycles, that's fine. 2 is going to 3, and so things are fine so far. 3 is going to 4. Now say 48 is going to 49 in this 100 cycle, and 49 is going to 50 in this 2 cycles. So 48 is basically going to 50 in xy. Okay, now 49 is going to 50 in the 100 cycle, and 50 is going to 49 the 2 cycles. So basically 49 is fixed under this 2 cycle. Now 50 is going to 51 in 100 cycle, and 51 is fixed here. So then the thing continues, 51 going to 52, blah blah blah, and then 100 is going to 1. So now we have identified what this permutation is. Now let's write the product of disjoint cycles. So 1 going to 2, 2 going to 3, 3 going to 4, things are fine. 47 going to 48, but 48 is going to 50, and then you skip, so 50 going to 51, and 52 dot 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 till 100. Okay, and what is the number missing here? 49, okay, which is fixed, so that's it. 49 is fixed, so we don't need to write that. So basically this permutation is this cycle. So then we have to just find the length of this cycle, and that will be order. So all the numbers are there from 1 to 100 except 49. So the length of this cycle is 99, and so order of this element will also be 99. Okay, so this question is from JAM 2019, and it asks what is the size of this set. So what are the elements in S3 such that when you take g to the power 4, that is you compose g with itself 4 times, you get the identity element. Okay, so for that let's look at the elements of S3. S3 has 6 elements, and you have 2 3 cycles, 1 2 3, and then 1 3 2. Then you have 3 2 cycles, so 1 2, 1 3, and 2 3, and then you have the identity element. So these are the 6 elements. Now these 3 cycles have order 3, these 2 cycles have order 2, okay, and identity has order 1. So this means that these elements satisfy g to the power 3 identity, these elements satisfy g to the power 2 is identity, and this is basically g is identity. So you can see that if g cube has an identity, it means that g to the power 4 is g and not identity. Okay, so these elements can't be in this set. Now if g square is identity, then g4 will also be identity, right? So these elements can be in the set, and if g is identity, again g to the power 4 can be identity. So identity element is also in this set. So there are 1 2 3 4 elements in this set. Okay, so this question came in JAM 2021, and it asks what is the number of cycles of length 4 in S6. So this is basically counting problem. So you need to find the cycles of length 4, how many are there. So of course, if you want to make a 4 cycle, you need to choose first 4 numbers out of 6, okay, which you can put. Now, okay, so once you put, you can arrange them in 4 factorial ways. Now the question is, like, all 4 factorial ways in which you can arrange, are they all distinct cycles? So the answer is not. Why? Because consider 1 2 3 4. Suppose you got a 4 cycle like this. If you cyclically change them. For example, if you consider 2 3 4 1, then this is same, right? Because you can see that 1 is going to 2, 2 is going to 3, and 3 is going to 4, and 4 is going to 1. Same thing is happening here. 2 is going to 3, 3 is going to 4, 4 is going to 1, and 1 is going to 2. Again, if you cyclically change them, like 3 4 1 2, it is same, and 4 1 2 3 is also same. So once a cycle, there are 4 other cycles which are same, so you need to divide by 4. So the total number would be 6 factorial. 6c4 will be 6 factorial, 4 factorial, 2 factorial, 2 4 factorial over 4. 4 factorial cancels with this, and you get 6 into 5 into 4 into 3. 2 factorial cancels out, divided by 4. 4 4 cancels out, you get 6 5s are 30 into 3, 90. So there are 90 cycles of length 4. Okay, so this next question came in recently in Jan 2021, and it asks the number of elements of order 2 in the group is 4. Okay, so if we can know the cycle structure or cycle decomposition of elements of order 2, then maybe we can find what those elements are. So partitions of 4 are 4, 1 plus 3, okay, 1 plus 1 plus 2, and 2 plus 2, and 1 plus 1 plus 1 plus 1. Okay, these are the 5 partitions of 4. Now if this partition will have order 4, this will have order 3, this will have order 2, this will have order 2, and this will have order 1. So these are the 2 partitions, cycle decompositions, which can give order 2. Okay, so this is basically 2 cycles, right? Because 2 elements are fixed and you have 2 cycles. So what are the 2 cycles in S4? 1 2, 1 3, 1 4. Okay, then you can make 2 3, 2 4, then 3 4. So these are 2 cycles, they all have order 2. Then these are product of 2 cycles. Okay, all 2 cycles. So you get, for example, 1 2 and disjoint. So 1 2 3 4, okay, is 1. Then you can write next as 1 3 and 2 4. Then the third I can write as 1 4 and 2 3. And you can see that these are all possible permutations of 2 plus 2 type. So how many elements you get of order 2? 1 2 3 4 5 6 7 8 and 9. So there are 9 elements of order 2 in S4.